righty. Let me find my notes somewhere all in here. All right. So we are moving to the exciting world of gas stoichiometry. Yay. Remember, since it has something to do with stoichiometry, you are probably going to need a balanced equation for the mole to mole ratio, because that's what makes something stoichiometry, is that you have to eventually use that mole to mole ratio to get from your known to your unknown. The other thing that you are going to use in these problems are the ideal gas law. So you don't need to write this down. I'm just going to jot it down. Here's my ideal gas law. If I look at the ideal gas law and then I think about stoichiometry, which part of the ideal gas law would kind of go along with stoichiometry? Moles, exactly. So sometimes you're going to have to use stoichiometry to get the moles of a gas and then plug it in the gas law to find something else, or vice versa. So they're a little bit long. In AP chemistry, do I have anybody taking AP chemistry? Where are you moving to? You happy? Yeah. You could probably take AP chemistry there. They probably offer it too. Maybe even more. But anyway, I wish some of y'all would take it. We have a good time. And if you would talk to some people that are actually taking it, because the theory is it brings down your GPA, but I have people that are doing the work that have kept a very high keep a very high GPA. Anyway, AP chemistry loves this. They love to make you like use stoichiometry and the ideal gas law like 2 times each, like on the main test. So, all right. So the other thing that we're going to be using in some of these problems is the molar volume. And the molar volume, which is in liters per mole of a gas, depends on the temperature. Oh, that's something's not spelled right on that. Maybe. I don't think it's okay. And pressure of the gas, not its identity. So in other words, I could have 2 very different gases. I mean, they could have way different molar masses, but if I'm comparing them just per liter, they're going to have the same moles. If the gas is at STP, then that amount is going to be 22.4 liters per 1 mole. That is called the molar volume, or the volume of ideal gas, and it's true only when the gas is at STP. And that is on your reference sheet. Some of y'all have already tried to use it on something, but we haven't actually done it yet. So right in the middle where it says you're 22.4. That's where I'm getting that from, but it's only true at STP. So think of it as a conversion factor. If you're at STP and you can use this, it makes it a little bit easier. You probably won't even have to use the ideal gas law. So let's look at a few of each. So if it says the gas is at STP, or standard temperature and pressure, then you're probably going to be able to use this conversion factor. Under any other conditions, the ideal gas law, PV is equal to nRT, is going to be the connection that you're going to need to make between the stoichiometry and your moles of your gas. Remember that only a gas can go into the ideal gas law. So like if they give me a description of the solid, they tell me how many moles of solid I have, I can't put that into the ideal gas law. I would have to use stoichiometry to convert it to moles of the gas. Only gases can go into the different laws that we've done. All right, so let's look at a few examples. I'm going to move this up just a little bit. All right, it says what volume of hydrogen is produced by the reaction of 36.5 grams of magnesium, which is a solid piece of metal, with excess hydrochloric acid in an aqueous or water solution at standard temperature and pressure. So the first thing that I notice, it's at STP. I'm interested in volume, so I should be able at some point to use 22.4 liters per 1 mole. Just kind of get my mind thinking about that. The other thing that I need is I need a balanced equation because I'm given information about solid, but I'm trying to find something about a gas. So this kind of tells me what their reaction is. It says that I have magnesium plus hydrochloric acid is going to give us hydrogen gas. It's the only gas I have. And then the other thing that would be left would be my magnesium chloride, MgCl2. So that's just a single replacement reaction. The only thing that I have in there that is a gas is my hydrogen. Magnesium chloride and magnesium are solids, and the hydrochloric acid's in a water solution. I would need to do some quick balancing, which is a 2 right there. I think that's the only thing that I need. All right, so it says that I have 36.5 grams of magnesium with excess hydrochloric acid. Remember, that's just telling me that it's not a limiting reactant problem. So I'm not worried about hydrochloric acid in this one. There's a whole bunch of that. So I'm gonna start with what I'm given, 36.5 grams of magnesium. And I eventually want to get to, I eventually want to get to volume of hydrogen gas. So that would be in liters. So down here, I want to get to liters of hydrogen. So on these, I can't necessarily tell you it's always going to be 2 steps. It's always going to be 3 steps. You're just going to have to kind of work with it as you go along. But since I have my liters down here and I'm at STP, I should kind of start thinking, okay, I'm probably not going to use that 22.4 till the end because that's my conversion when I try to get to liters. So the first thing that I need to do is I need to get from grams of magnesium, which is my known, to moles of hydrogen. So that's how I'm going to start it. So I need to convert grams of magnesium to moles of magnesium. So I would use my molar mass, 24.31 grams. That's just straight off the periodic table in 1 mole of magnesium. If I stop right there, I'm still dealing with magnesium. I want to be dealing with hydrogen. So this is where I'm going to use my mole to mole ratio. So this is where I'm going to go from moles of magnesium to moles of hydrogen. So that's just my coefficient. And in this case, they both just would be 1. And then I keep on following my units, moles of hydrogen. I would be moles of hydrogen down here. But like I said, we're at STP and I see that liter. So I'm going to use 22.4 liters per 1 mole. The 22.4 always goes with the liter unit and the 1 goes with the moles. So if I do a quick cancel out, I see that everything cancels out but liters of hydrogen, which is what I wanted. So now you just need to put it in your calculator and adjust for sig fig. So how many sig figs would we have at the end here? 3, exactly. 33.6. That's what I got to. 33.6 liters would be your units. Anybody have any questions on that one? All right, so let's look at another one that is not at STP, and you'll see that these usually are a little bit more trouble, a little bit more work. All right, and are we good? I'm gonna move this up. All right. So we're still using the same equation. I'm just going to rewrite mine because I bet y'all probably can still see yours fine. All right, so I had Mg plus 2HCl H2 plus MgCl2. All right. So now it says what volume of hydrogen. So I'm trying to find liters of hydrogen. That's what I'm trying to find. Is produced by the reaction of 36.5 grams of magnesium with excess hydrochloric acid. Once again, that just tells me I don't have to worry about the hydrochloric acid And then I have a temperature and I have a pressure. It is not at STP, so I can't use 22.4. That usually makes it a little bit quicker. All right, I eventually want to use PV equals nRT, but I have 36.5 grams of magnesium. That's a solid, so it can't be like what we did in the warm-up. I can't just convert that to moles and plug it in. So what am I going to have to do first on this particular one? Stoichiometry or ideal gas law? Well, the only problem with ideal gas law is I would have two unknowns because I'm trying to find volume and I also don't have moles. Yeah, so if we think about it, if we use the stoichiometry first, I could do a gram to mole problem and get to moles of hydrogen. And then I would have everything I need. So I'm going to start with 36.5 grams of magnesium. And I want to get 2 moles of hydrogen so I can plug it in that gas law because I have everything else. All right, so these are always 3 steps. So I'm going to start by using my molar mass of my magnesium, 24.31 grams per 1 mole. And to get from moles of my known to moles of my unknown, I'm going to use my mole to mole ratio, which neither one has a coefficient. So 1 mole of magnesium per 1 mole of hydrogen. All right, I'm eventually going to need 3 sig figs. So I want to be sure I keep this answer at 3 sig figs when I do this side calculation. Some people are going down to like 2 or 1 sig fig here, and then it messes you up later. All right, so 36.5 divided by 24.31 gives you, what do we get for moles of hydrogen? Perfect, 1.50, and that is moles of hydrogen. But we want liters of hydrogen, so that's now where I can connect it to the ideal gas law. So now I'll use the ideal gas law, so my pressure is 730. Oh, yes, torr. I'm trying to find my volume. My moles is why I had to use my stoichiometry. Since I'm using torr for my R, I'm going to use this man. And then my temperature would be 25 plus 273, which is 298 K. All right. So solve for my V, which means I divide all this by 730.5. And that should tell us how many liters of hydrogen. Perfect, 38.2 liters. That is finally my answer. So that's kind of the different problems. We're going to look at some more on practice, and sometimes they're like arranged in a different, but it's kind of like a puzzle to me, although I mean, I know I'm nerdy with regards to chemistry. So, but to me, it's like you have to read it and try to figure out, you know, which goes first, which goes second, you know, and what I'm using. But just one big thing is remember, if they give you some information about a solid or even a liquid, that can't go into the ideal gas law. So that's the whole point. If you're given information about a solid or liquid, you have to use your stoichiometry to make that conversion. All right, anybody have any questions on that? All right, if you'll pull out your practice you picked up today, I'm gonna do a few of those because there wasn't a whole lot of examples there. So tomorrow we will just keep on working on stoichiometry. We're not having a separate quiz over it. You'll just see it on the test, but try to work some at home tonight. That way, if you have questions, you can come back with those questions tomorrow. Practice and probably end with maybe a lesson check. But yeah, just mainly practice because this is kind of one of the harder things that we've probably done. All right, I've just picked out a few here and there that I think are good representations of what we're doing. So we'll just start with number 1. All right, I got my nice balanced equation. I know everybody likes that. I'm trying to find liters of water vapors. So I'm trying to find my volume of water vapor can be made from 50 liters of oxygen gas. And once again, I have that excess hydrogen, which just tells me hydrogen is not part of this, at STP. So once I see STP, I start thinking to myself, all right, I'm probably going to have to use 22.4 liters per 1 mole. So I have liters of water and I'm given liters of oxygen. Because it's at STP, I don't have to use the ideal gas law. I can connect them with this. So I'm just going to start off with my 5 liters of oxygen. And down here, I eventually want to get to liters of water vapor. And I'm at STP. So I noticed that I have liters here and liters down there. And the only thing we've used for conversion factor is that 22.4 liters per mole. So just from this setup, I'm seeing I'm probably going to have to use it twice, which you can do. That's fine. So we're going to follow our units. I'm liters of oxygen here. So I need to be liters of oxygen down here. Since we're at STP, I can say there's 22.4 liters per 1 mole. That's information about oxygen. I want to get to water, so that means I'm going to have to use my mole to mole ratio. So my known is oxygen, no coefficient. So I have 1 mole of oxygen for every 2 moles of water. And then I follow my units, moles of water. I got to be moles of water down here. I see that I want to get it to liters. Once again, at STP, I can say 22.4 liters per 1 mole. The 22.4 always goes with the liters and the 1 always goes with the moles. So multiply across and divide by the, you probably don't even need your calculator for this. Why do I say that? Right, because this and this can cancel out. So really you just end up with 5 times 2. 10. So how do I need to write 10? So I have 2 sig figs. Yeah. And that's liters of water. We get so dependent on our calculator. I like to just grab them. And 3 plus 2. All right. Anybody have any questions on that one? Why we did it? Do we really care about how many liters of water? Do you see? Look on the back side, right in the middle, kind of. It says that volume of ideal gas at STP. That's 22.4 liters per 1 mole. But you only can use that when you're at STP. See, so like on this one, if we weren't at STP, then that's when they get longer. And I probably would have to use some stoichiometry, like to get to my moles of water and then plug that into my ideal gas law. So if you're at STP, it should make these problems shorter. That's the idea behind that. All right, let's look at another one. I think we will jump down to number 3. Just picked out some here and there that were pretty good representations. All right, this is still using the same equation, so I'm just going to rewrite mine. Y'all can still see yours from the top. So 2 water, no, not water, 2 hydrogen plus oxygen gives me 2 water molecules. All right. So how many liters of water? So I'm eventually trying to find my volume of water can be made from 55 grams of oxygen gas. Once again, excess of hydrogen just tells me I don't have to worry about it. Pressure of 12.4 atmospheres, and there is my temperature. So I'm not at STP, so I can't use 22.4. I can't use that. All right, so I have grams of oxygen and I want to find out information really about water. So what do you think that you're going to have to do first? Stoichiometry or ideal gas law? Stoichiometry, exactly. I could hurt you. Mother can. So like when my kids were talking about me behind my back, I could hear. You can ask my oldest daughter about that. She never got in trouble. And the one time she called me a name, I'll let y'all figure out what she probably called me. She thought I could hear. Anyway, so I'm going to start here and I'm going to go to from grams of oxygen to moles. So that's going to be a 3-step. I have 55 grams of oxygen and I want to get to moles of water. And then once I have moles of water, I can use the ideal gas law to get to my volume, my liters. So this is just stoichiometry. Grams, like on our warm up today, it's diatomic. So I'll say there's 32.00 grams in 1 mole of oxygen. And now I need to do that connection step with the mole ratio. So oxygen doesn't have a coefficient. So 1 mole of oxygen gives me 2 moles of water. And like I said, this is like a side calculation. I got to keep it at least those 2 sig figs. So when you did that point, you should get 3.4 moles of H2O. See, if we were at STP, we could go one more step and use that 22.4, but we're not. So now we have to come back and use the ideal gas law. So I'm just going to jot that down. You don't have to if you don't want to. But now we have everything we need. Pressure, volume is what I'm trying to find. Now I have my moles, my R, and my T. So the point of doing the stoichiometry first was so you can get moles of your water. So now we're just going to plug in. My pressure is 12.4 atm. I'm interested in my volume, my moles, 3.4 moles. Because I used atmospheres, I could use the 0.0821 and my temperature, 85 plus 273 is 358 K. All right, you end up having all 3 of these divided by 12.4. And our answer, because of that 55 grams, can just have 2 sig figs. So you're hoping that you get 8.1. Huh? All right, any questions on that one? And, you know, it's just attacking these and, you know, doing a little practice to see what you need to figure out. All right, let's go to number 10. Yes, sir. It's just 2 because of this 55. That's only 2, so that limits everything else. Yeah, you're right. Some of the other ones are 3, but you always have to go with that smallest. 8.1 should be the right way. Don't forget your practice has your, when you round it, should be 8.1. So because the 5 is behind the 0, you would round it up to 0.1. All right, let's go down to number 10. It's just a little bit different type of problem. And all right, good old combustion reaction. It says balance the above reaction. Nicer than me. I probably just give you the reaction. Hope you figured out you didn't balance it. 2, 25, 16, and 18. So if you look at that one and you go back to when we did combustion reactions, if you were balancing that, what would you probably have to have done? A little trick. On our combustion reactions, you probably would have started balancing it because you need 8 carbon. You probably would have started with 8 here, right? Yeah, and then you would have come to that point where you had to do 2. And you can tell that because there's a 2 here. All right, there we go. Nice balanced equation. We have 3 gases floating around in that. How many grams of water would be produced if 20 liters of oxygen gas were burned at my temperature and my pressure? All right, so I have all this information about oxygen. And then I need to get that to grams of water. So on this one, it's not an STP. I can't use 22.4. So what are we going to use first on this? Stoichiometry or ideal gas law? Okay, if I use stoichiometry, well, if I have all this information right about oxygen, will any of that information about oxygen somehow get me to grams of water? Okay. So, but that means that I'm using which one first? No, I don't. On this one, you're gonna have to use ideal gas law first. After the bear, you won't even have to do that. Yeah, you won't have to do that. But because I have all this information about oxygen, can't I use the ideal gas law to figure out moles of oxygen? And then I have a balanced equation. So then can I go from moles of oxygen and get to grams of water? Yes. So this one's just a little, like I said, it's a puzzle. So I'm going to use ideal gas law first. So 1.3 atmospheres. My volume was 20 liters. I'm interested in the N. That's usually what you're interested somehow on these. 0.0821, only one that I remember off the top of my head. And 263 K. All right, all of that to get my moles of water. So 821 times 263. Not moles of water, I'm sorry, moles of oxygen. So how many moles of oxygen did we get? 1.2 moles of oxygen, but I'm not finished because I want to get 2 grams of water. Luckily, they are in the same balanced equation, so I can do a mole to gram problem, which we know is 3 steps. And that'll get me 2 grams of water. So I start with my 1.2 moles of oxygen, and I want to get 2 grams of water. So first thing on this one is I have to use my mole to mole ratio for my coefficient. So 25 moles of oxygen for every 18 moles of water. And then follow my units, moles of water. I'm going to be moles of water down here. And I need it in grams, so I would need a molar mass. You may have the molar mass of water memorized. 18.02 grams per 1 mole. If I do a quick oxygen is 16 and each hydrogen is 1.01.
No, like on the second box where it says 1 more.
Oh, whoa. On the second box where, oh, yes, I did. I said it and didn't write it. Thank you. Sorry about that. I'm confused too. Yes, thank you. I got confused between the yes. All right, and hopefully you will get your answer in two sig figs of 16 grams. Puzzle. Is it fun? Sometimes in AP chemistry, like they love these problems, and sometimes you may have to use like the ideal gas law twice instead of stoichiometry once, or like, I don't know, sometimes they like to use these like little. Yes, make it extra fun. All right, so tomorrow we all are going to continue with practice. I really wish that you would try some at home so you can come back with good questions. That would be helpful. Y'all also remember, help me remember to divide up y'all up into your two teams. So I'm not for sure who my sub is on Thursday. I can't remember if I got Mr. Anderson or not, but. And then we'll do the review game on Friday.